Hey everyone, this is a video lesson that I'm using in my AP Calculus AB class, and I'm putting it online in case it would be helpful to others as well. This is the second video for this section, and in this video we are going to talk about approximating change with what is called differentials. There is a link to a printable set of guided notes that you can use to follow along with the examples that I do in this video in the description of the first video for this section. All right, let's get back to where we were in those notes. Actually, no, I just remembered I have an additional little warm-up problem and a random zero. That's now gone. Okay. I have a little warm-up problem that's not in the notes. I just want to talk about this for a minute to sort of set the stage to understand differentials. Okay, take a look at this problem that I use in my Algebra 1 class. At Custom T-Shirts, when a customer places an order for a special design, Custom T-Shirts charges a one-time fee of $15 to set up the design, plus $8 for each T-shirt printed. Okay, so one of the first things that I ask my algebra students whenever we do this problem together in class is, how much does it cost for one shirt? And they look at the numbers and they say $23, right? And I say, yes. And then the next thing I say is, how much does it cost for an additional shirt? Now you're buying two shirts. And a lot of them figure out that you're not going to say $46. You're not going to double it because this $15 is a one-time fee. So you are just adding an additional $8 for each t-shirt printed, right? Okay, so I'm going somewhere with this, I promise. That additional $8 for each t-shirt printed is a rate of change, right? It is the slope of this linear function that we're working with here. We could write this equation as y equals 8x plus 15, where y is the total cost and x is the number of shirts being bought. And, we could say that the slope or the change in y over the change in x, right? Slope can be written like this, delta y over delta x is 8 or 8 over 1. And we have all sorts of conversations going at that point in an algebra class, centered around what is slope, what is this additional number in relation to the graph, all fun things. Like, I'm thinking back, I'm like, yes, I love teaching this stuff to algebra students. All right, but I love teaching it here, but it's a little bit different as we move into calculus. Okay, what we need to be able to do is take this idea of a slope being a rate of change and apply that to derivatives. Okay. So what I want you to recall here, let's see exactly what I want us to write, because I have it written out nicely. Yep, look at this. Remember, derivative can be thought of as the way that you find the slope of a curve. Let's just write slope. Okay, so slope can be written as this formula, which I'm sure you've seen before. Or it can be shortened to this formula. Okay, and this means change in. Change in y over change in x. That's what that delta means. All right, now that's slope of a line, right? That's slope of a line. Here, though, with derivatives, we're working with an additional kind of slope. Slope of a tangent line or slope of a curve, which is the limit of a slope. Does this look familiar? It's been quite a while since you've seen this, right? We're not working with this limit again, just so you know. If you're thinking, oh no, I am not going back to that again. No, we're not. Okay, but I'm going somewhere with this. Or we could shorten this to dy over dx. Okay, and what I hope you're seeing are the similarities. We have this slope formula as delta y over delta x. We take the limit as h approaches 0 of that formula where h is defined as the distance between the 2 points, And what comes out of that is dy over dx, and that changes this from change in to infinitesimally small change in. Infinitesimally small change in. My brain is so happy right now that I was able to say that word. Okay, so far you've looked at this dy over dx notation as just that. It's just been notation. It's been a way to denote a derivative, and that's really what it is. However, we can use dy and dx separate as variables, and we can use them to approximate change in a function. Okay, now this is just an approximation technique. It is not exact, and so that's why I say, dy over dx is a notation, but we can look at it as something else if we want to approximate change. And that's called using differentials. Here's your definition for differentials. If you have a differentiable function at x equals a, then you can approximate the change in the function values when x changes from a to a plus dx by using this formula, df equals f prime of a times dx. Okay, so as usual, I would suggest you pause the video to take that definition down in your notes. But also, as usual, I'm just going to move right along and, probably forget about that way that we're looking at the formula and just show you how it works here with example 3. Find the differential dy and evaluate dy for the given values of x and dx. Okay, so we have a function here, y equals x to the 5th plus 37x. We have an x coordinate that we're starting at, and then we have a dx value. And this dx value is how much your x coordinate is changing by. So we could say, let's add that on. And, we would get 1.01 and find what the new function value is. And then find the change from the old function value to the new function value. Or a way that we could do that a little bit quicker is we could say, let's take the derivative, which is 5x to the 4th plus 37, and use this equation with these values to approximate that change. Okay, in order to do that, you want to multiply the dx over to the other side. That's a little bit of a cringe statement right there because, technically this is not exact, okay, but it works. And then we would sub 1 in for the x's, or 1 in for the x. There's only one x. Why do my 4's look like that when I write with this pen? And we would sub 0.01 in for the dx. And what we would get out of that is a dy value. And that would be, I'm just going to, just to save some time, I'll tell you. When you plug that into the calculator, you get this, 0.42. And that is called calculating a differential. Okay, let's do a couple of other examples with functions, and then I'll show you where this can be applied. So here we have y equals sine of 3x. The derivative of that, dy over dx, is 3 cosine of 3x, right? With chain rule, the derivative of sine 3x is cosine of 3x multiplied by the derivative of 3x, which is 3. Now, this is saying when we start at x equals pi, but we go down by 200ths in that x, what happens to the change in the y? That's what you're trying to find. What happens to the y? How does the y change? In order to do that, we are again going to move the dx to the other side. And sub in the values given to us. I think this one is kind of fun because it shows that for this function, sine of 3x, around x equals pi, if you decrease the x by just a small amount, the y increases. What I'm going to get out of this is 0.06, which is a positive amount, and that means the y is going up, which would make sense if you look at the function, the direction of the function. Okay, so next there's a u-try where, again, we're just working with a function here, an x value, and it gives us two different dx values. You're just supposed to do two separate calculations, one with when dx is 0.01 and another one with dx is 0.05. I would suggest you pause the video now and you try that. I'm going to do the same, and then I'll come back and show you the answer. Okay, as promised, here's the derivative. Here is the derivative in differential form, and here's the calculations that you need to find the differential of y when dx is 0.01 and the differential of y when dx is 0.05. Okay, and I think this one's kind of cool because you can see that for a very small amount of change in the x, the y changes by a relatively high amount, right? And if you know anything about exponential functions, that would make sense. Okay, so that's all fun and good because it's pretty easy to do, right? But where can this actually be used? So if you change the radius of a circle from 10 to 10.1 meters, and you want to know what is the change in the area of that circle, you could do a calculation known as delta A. You could say, okay, I'm going to find the area of my circle when it is 10.1. I'm going to find the area of my circle when the radius is 10. And then I'm going to subtract them. Final minus initial. Right? And that's called delta A. But that's doing more calculations than what are needed if you don't need an exact value for your change. Okay, so what you can do instead is you can use differentials. Take a look at example 4 with me. The radius r of a circle increases from 10 meters to 10.1 meters. Use dA to estimate the increase in the circle's area. Compare this estimate with the true change delta A and find the approximation error. Okay, so let's do our differential work over here, and we'll compare it to our true change delta A work over here. Okay, so let's do dA. So if we have the area formula for a circle, which is pi r squared, the derivative of it, which we can write as dA over dr. This is the derivative of the area with respect to the radius. Okay, watch this. It's so cool. The derivative of this formula is 2 pi r using the power rule, right? The 2 comes down, take one away to get your new power. Okay, do you see why this is so cool? It's cool because we just took the area formula for a circle, we took its derivative, and we ended up with the circumference formula for a circle. Yes, there's a mathematical reason behind that, and I explain it in a little video I did once, but I'm not going to go into all that now, but it's very exciting to me, and I hope it's exciting to you too. Okay, let's keep going now with our differential by moving the dr over to the other side. And now let's fill in our values. The r that we're going to use here is the original radius. The dr is the change in the radius. So that would be 0.1. Okay, what did I just say? Oh, the radius is 10 and the change in the radius is 0.1. Okay, and this ends up to be 2 pi, right? Or let's put it in decimal form to be able to compare with our other value, our true change. Let's say 6.283. There we go. Okay, so what we just did was we approximated the change in the area. If you change the radius of a circle by just 1/10 of a meter, the area, oh, I should have units. The area is going to change by a little over 6 square meters. That's what we found. And again, this is an approximation of the change. What I now want to do is compare that with delta A, where you find the actual change. Okay, to find the actual change, let's find the area of the original circle, which is 100 pi. Yeah, actually, you know what? We don't need to write all that out. I'm like, my brain's going, why are you writing it out like that? Let's just write it like this. I'm sorry. Okay, let's write it like this. To calculate the true change, what we would need to do is we would need to say what the area of the circle is at 10.1 and take away from that the area of the circle at 10 meters. Okay. And again, just to save some time, I'm not going to type that into the calculator to show you the answer. I'll just tell you that when you do that, you should get 6.315 if we go to 3 decimal places, and that is again square meters. Okay, so you can see that our approximation of the change was pretty close. If you go to the 10th place, it is the same, but it is slightly off. And so what we can do is we can find the approximation error. And, you know, just to review that one more time, to do that, you are going to take the absolute value of what you found minus the exact divided by the exact to get relative, and then I like to multiply it by 100 to get it into percent error. And that is approximately 0.5% error. I don't know if I'll write that down here. It's getting cut off. Half a percent error. Oh, I should say error. There you go. And so that's one place where differentials can be applied. That's a little bit more concrete. You can apply it anywhere that you want to approximate a change. Okay, let's look at a couple of other examples. This one is where we are looking at the circumference of a circle, okay, because we are inflating a bicycle tire, which changes the radius from 2 inches to 3 inches. Now, what you're going to find with circumference, okay, if we're starting with that formula, is that when we do the differential, we get a constant, right? And if that's the case, I mean, this is a linear function, right? That is the true change. That's the absolute change because it is a constant. This is your slope of the line. Okay, so we're not really estimating in this case. We are finding the exact answer. You know, let's go into our form where the dr is on the other side, and then the dr would be 1 because we are changing the radius from 12 to 13. And so we get out of that, again, 2 pi. I'm just going to leave it as 2 pi this time. Okay, this example is here actually just to talk about these different words: absolute change, relative change, and percentage change. You know, how do we find all of those things? Well, what we just found here is absolute change. It's just how much did it change? Relative change is where you say how much it changed in relation to, or in a ratio to, where it started. So the original circumference is 24 pi inches, right? So if we took 2 pi over 24 pi and we reduce that, that's 1/12. That's our relative change. And finally, we could multiply that by 100, and that is 8.3%. And that's how you get percent change. Okay, finally, I think example 6 is super fun. And this is the last one that I'm going to go over. I will give you an answer to example 7. I don't think it's fun, so I'm not going to really go over it. Okay, but let's finish with one that's pretty fun. Okay, suppose the Earth were a perfect sphere and we determined the radius to be 3,959 plus or minus a tenth miles. The question is, what effect would the tolerance of minus a tenth have on our estimate of the Earth's surface area? Okay, so this is saying if we are off in our estimate of the radius of the Earth by just a tenth of a mile in either direction, meaning over it by a tenth or under by a tenth, what effect is that going to have on how far we are off by the surface area of the Earth? Okay, in order to do this, we need to get the surface area formula for a sphere, which is 4 pi r squared, right? Okay. And we're going to take the derivative of this to then get the differential equation. Okay, so dSA over dr is 8 pi r. Move that dr to the other side. And now we're ready to fill in our values. What values do we have here? Well, the radius of the Earth is estimated to be 3,959. So that goes in for the r. What is the dr value? It is 0.1. Okay. The plus or minus, is just meaning it could go in either direction. So we can put the plus or minus back into our final answer, but we can leave it out for our calculation here. Okay. So finally, doing this calculation, we get that the change in the surface area is going to be approximately, doing this calculation, plus or minus 9,950.1 square miles. That's how much the surface area could be off by just a tenth of a mile off in our reading of the radius of the Earth. I think that's pretty fun. Just to give you some perspective, that's approximately the size of New Jersey. So really, we could say the answer is plus or minus New Jersey. Perfect. Put that on your AP exam. No, okay. All right, like I said, I wanted to end with a fun example, and so I'm not going to really go over example 7. If you want to try it, you can, but I'll tell you that there is a piece of missing information. It is the initial time, and that just means that you leave your answer in terms of the variable t. I'll pause the video, show you the answer, but again, I'm not going to give too much of an explanation because it is pretty much the same thing. Okay, here's the final answer, which says that your calculations will be 3.2, the change in your calculation, I should say, would be 3.2 times the time. Okay, everybody, that is it for section 4.5 on linearization and differentials. It may seem like you saw two very different things in this section, linearization versus differentials, but keep in mind that both of them are ways to use derivatives for approximations. Linearization is how to use derivatives to approximate actual function values. Differentials is a way to approximate the change in the function value. As usual, I hope this was helpful. Bye.